Hello everyone, my name is Barnaba. I'm a C++ developer currently working at Ericsson with some previous experience in the automotive industry. I will be talking about fuzzing class interfaces for generating and running tests with libFuzzer. This was also the topic of my master's thesis that I recently finished. My invaluable professor and supervisor Zoltán Porkolab came up with the base idea of it. Before we get into it, let me present the outline of what is to come. I will start by showing through example what is missing from the current testing ecosystem and why we should not be satisfied by using only unit tests to test our classes, even though they are great too. After that, a brief introduction of fuzzing in general and Clang libFuzzer will follow. Then, we will go through the design of using these to create a newer testing method which is meant to test our classes based on their interfaces only. Then we will finish off seeing the results we've achieved with this interface fuzzer in two brief case studies. Let's start by following the design and testing of a container class and see where it takes us. Let's suppose that we would like to implement a double-ended queue, something akin to stud queue, This container works by having vectors of static sized arrays, one vector in fact, and if it needs to grow to either direction, it can increase the size of the main vector. This is how the interface of set class looks like. It's not templated for the sake of simplicity. We have our pushback and popback methods. We can query the element on the back, and we can also do the same things on the front as well. We, of course, can also access the number of elements currently contained within. Now let's pretend that we finished the implementation of the class and are very eager to test it out. Let's see whether it works or not. What we would do is that we would write unit tests for it, just like the one on the screen. I have used Google Test for the sake of this example, but I imagine all unit test frameworks to be quite similar. This test is great because we are only testing a small part of the software in isolation, which makes it far easier to find the root cause of an issue if we encounter any. One very important observation for the sake of this talk is the structure of the unit test. It's practically a list of method calls with status sanctions in between them. But the million-dollar question when it comes to unit tests is when to stop testing. How many test cases are enough? Maybe we should just write similar for the frontal methods as well, and that's it. Now, of course, that wouldn't be enough. There are a lot of possible undetected bugs which we need to care about. In the following slides, I've drawn the arrays to have only 3 elements, but in reality they tend to have 16 or so. The main vulnerability of this container is the management of the arrays contained within the vector, just like creating one, which is shown on the screen. Or maybe creating the one is done well, but when we have to destruct an array, we somehow fail to delete it. We cause a memory leak. Or it's also possible that after the destruction of an array, we leave the object in an invalid state. And that might be only discovered after recreating the previously destructed array, leading to a crash, for example. And what's particularly insidious about this case is that covering it gives us 0 additional line of code coverage. And it's very easy to forget about. And we see that white box testing is very hard. Let's try the black box approach where we don't care about the implementation. How can we proceed after a queue is constructed? First, we have 3 methods we can use. We have 3 legal options. because of course the queue is empty, so we either increase it to one direction or to just query the size of it. But if we decide to call push front, the number of possibilities explode, showing 7 new ones now. And here we have lots of possibilities. Maybe we call pop front, we return to the deck having 0 elements and having 3 different options now again. But if we call a pushback again, it reveals the same 7 possibilities like before. And what we can observe from this tree is that the number of total paths that we can take is exponential with regards to the number of method calls that we would like to do. And this practically means that exhaustive testing is impossible. We simply cannot possibly test all the method combinations up until a certain amount of calls. There's just too much. And another thing which complicates it is that we still need to pay attention to the preconditions, right? We can't exhaustively test every single combination. We have to care about the method calls being legal as well. And so black box testing exhaustively is not very feasible, and white box testing is not ideal because, at least in my experience, most bugs arise from situations the developers don't think of. But if a situation does not come to mind, how would I include it in the test case? And this is why white box testing is not enough. And my supervisor has a great saying that I really like, and that's the fact that the difference between monkeys and programmers is that monkeys know when they should be using tools. And with it, he tries to convince me, and also everyone else as well, to be a bit more like monkeys and try using tools, right? When we need to. So for this tool, we should first agree on a set of requirements that the tool needs to fulfill in order to help us with our problem. And of course, disclaimer, let me please mention again that I'm not trying to say that unit tests are not worth doing. I'm saying that we would need to supplement them with something. Now, what we would need is something to combat the exponential growth that we face. And a good idea might be automatic test generation. Because with automatic test generation, we could test way more test cases than manually. Of course, we still couldn't test all of them, far from it, but it would be still far more. And we could generate test cases like this with 2 pushbacks, one after the other. Or we could generate a pushback and a pop front afterwards. Or a pop front and a pushback, right? If we are trying to generate test cases based on the interface of the class by itself, pop front looks legal because we have no idea when we can call pop front. The interface does not really contain it, at least from a C++ language sense it doesn't. Now, but of course we shouldn't be okay with it. It's not a valid test case. It's a waste of time to run it. And so a second good requirement would be filtering out invalid method calls. Now, how would we want to use this tool? A great way of using it would be to just running random unit tests, for example, while the CI/CD machine is idle, right? Let's not rest it too much. And to support this usage, being able to generate a test case and then run it right afterwards seems a quite sane requirement. So we should add it to the list. On the other hand, we would also like to be able to also persist test cases. Maybe we've run this test case discovery for a long time, and we found a great amount of good test cases. We would want to persist it later, and if a new commit comes, we can just rerun the same tests for regression testing. So this is another thing that we would want to keep in mind, right? But of course, we don't want to save literally every single test case that the automatic generation creates. That would be simply way too much, a waste of space on the computer, right? And that's mostly because these are automatically generated test cases. It doesn't matter how smart the generation is, there would be some redundant test cases like the two on the slide right now. Both of them are only calling the size method on an empty container, and the size method is also a constant method, and we expect it to not change the container's state, right? So persisting only one of them would be ideal, and of course, if we can choose, persist the smaller one. But all of this means nothing if we are just generating the same 3 or 4 test cases all the time. We are not even calling some methods. We want to achieve a high combined coverage. And now comes the question, what kind of issues would we like to catch? Of course, finding crashes is great. And it's relatively easy to find them because if we run on them, we crash, right? It's a great identification of an error. But if it would be great if we could if we could detect other things, other undefined behavior, or even logical errors as well. And those who are familiar with fuzzing might realize that it fits most of the criteria that we've established, right? We will get back to this slide in a minute to see that I'm not lying about it, but first let's quickly refresh our knowledge about fuzzing. So, what is fuzzing? If you would like to see a talk focused on fuzzing only, I recommend the one on the bottom of the slide. I will give you a few seconds to copy it because I'm not sure how possible it is with the streaming setup. Great. So let's see how a general template of a fuzzer looks like. So the main act of fuzzing is done by the fuzzer engine. And what this fuzzer engine does is that it generates a string which is used as an argument to the test subject, the target function. This is the function what fuzzing is actually meant to test. And if the function is run and the function fails, we can raise the error. We can see that we've caught a bug, right? But if it does not fail, the fuzzer engine can just retry with a newly generated string. And although this method may look quite simplistic, it's a great method. It's time-proven. It has found thousands of crashes in reputable repositories. Now, the fuzzer engine that I've decided to use is LLVM Clang libFuzzer. Let me please highlight the differences between the general engine and libFuzzer. First of all, libFuzzer maintains a test case set, which is called a corpus. The corpus consists only of test cases which were deemed interesting by libFuzzer. We can think of interesting as something revealing new coverage, but it can also mean other things like leading to a new comparison result. And libFuzzer does not generate the string absolutely randomly. It uses the previously generated strings and combines them with different mutational algorithms, with the reasoning being that interesting test cases more likely will combine into newer interesting test cases. Now, libFuzzer uses this function that the user has to define as a target. Of course, we can just call our own target function from it, so it's not a big difference. Now, if the fuzzing fails, we raise error just the same way as we would in a general engine, but if we do not find an error, we store the previous string if it was interesting into the corpus and then retry. Now, let's see libFuzzer in action. Here, our fuzzing target first checks whether the received string is at least 2 characters long and then indexes into them. After that, it also indexes into a third character without checking the newer size requirements. Well, that sounds like a bug, right? And if the comparison holds, we have a nasty crash where we somehow index into a null pointer thinking that it's an array of at least size 5. Now, what we have to do to use libFuzzer is that we only have to add -fsanitize equals fuzzer as a compile argument. We didn't even declare a main function, but that is totally fine since libFuzzer will link its own main together with our binary automatically. This main is what implements the libFuzzer engine, and we repeatedly call our test function, target function, sorry. After running the binary, we can see the segmentation fault on address 4, which most likely, right, corresponds to the innermost issue within our code, the null pointer dereference. But this is not all that Clang can give to us. Clang also has other useful tools that we can use, namely sanitizers. Sanitizers are compiler built-in error detectors with relatively small runtime cost, with relatively meaning between 2 and 6 times the runtime increase per sanitizer enabled. There are multiple different sanitizers available. Let's see which ones. Address sanitizer checks things like use after free and double free. Memory sanitizer mostly cares about uninitialized reads. Undefined behavior sanitizer detects overflows, divides by 0, and a number of other undefined behaviors that we may encounter. Lastly, thread sanitizer is all about finding data races. These can be turned on by enumerating the sanitizers with commas in between, after the -fsanitize flag. One thing to keep in mind is that address sanitizer and memory sanitizer both try to hijack the allocation functions, and so they are not compatible with each other. If you would like some additional info on sanitizers, I recommend checking out the talk on the bottom of the slide. I will give you a few seconds to copy it just to be sure. Now, after discussing the sanitizers, let's read the error message on the previous fuzzing example a bit more carefully. The UB sanitizer was the sanitizer that caught the segmentation fault. We can see that that's what it says on the bottom of the slide, right? But I didn't even include it in the -fsanitize flag. So what's happening here? Well, what's happening here is that it is included by default with libFuzzer. That's all the secret that there is to it. But let's see whether we can actually catch the first bug in our code, the part when we are not checking whether the data is at least 3 characters long. And as you can see, memory sanitizer is the sanitizer for checking uses of uninitialized values, and it indeed does catch the bug. And this is great, right? These are perfect tools that we can use to supplement our vision. So let's get back into the slide, just as I've promised. Now we can verify that fuzzing indeed does generate test cases automatically. Of course, the second point does not really make sense when it comes to fuzzing, right? Fuzzing is all about testing string interfaces. It has no concept of method calls at all. Fuzzing runs test cases on the fly, every single fuzzer as far as I know, and libFuzzer maintains the corpus as a directory on the fly system, so persisting test cases is also taken care of. libFuzzer also has the ability of rerunning tests from a previously generated corpus. Filtering redundant test cases is also done by libFuzzer by simply not even saving them onto the corpus directory. Now, of course, libFuzzer also can achieve great coverage. As I've already mentioned, fuzzing is a great tool for that. And what about finding more things than just crashes? Well, we've seen that sanitizers work with libFuzzer, and so we can find more than just crashes, but logical errors seem a bit out of reach for fuzzing, right? But even still, fuzzing seems pretty great. It fits most of our criteria. Let's try to adapt it. But how? Because fuzzing is for string interfaces and we don't have that. What should we do? Right? This is how fuzzing looks like. What we have to do is sometimes take the string and transform it into something which we can use to test the fuzz class. What we have to do is that we have to somehow interpret the generated fuzz string as a method call list. And afterwards, we can just call the method call list one after the other on the fuzz class. Now, of course, if we would have reflection, it would be a great candidate for implementing something like this, right? If we could somehow query the methods that the class has and then use it afterwards. But reflection is pretty far away at the moment, at least as far as I know. So instead, what we have to do is that we have to use some user code to generate an interface description. And now, what the interpreter can do is to use that interface description to interpret the string and generate the method call list in the end. Now, what do I mean exactly by interface description? First of all, I've implemented a prototype of this outline tool, which has the name Autotest. I'm not exactly sold on it, but this is what came to mind first. And this is how the interface description looks like. I've chosen snake case for user code and Pascal or camel case for the library itself to easier differentiate what we have to do and what is already written for us. So what we can see is the description is just a bunch of method names one after the other. Some of them has const fun macros, some of them only has a fun macro, but if you've ever used Google Mock, it may look quite familiar to you. But does it actually convey all the information that we need? Of course, it shows us that we have size, which is a constant function. We have popback, which is not a constant function, but this is not enough, right? We have to be able to define the preconditions. Otherwise, how should we know which one we can call with an empty container? And here, what we can do is that we can define lambda, which signifies that the object is not empty, right? It takes a constant reference of the object and returns whether it is empty or not, quite easy. And this lambda, or any other functor taking the reference of a class and returning a bool, for that matter, can be used to define the precondition of a method. And this is great, right? Now we've passed the place when we would like to call invalid methods, because we can define every single precondition that we would have like this. But the other problem is that how should we know that pushback has arguments, right? And for that, I've created the definition of an argument placeholder, which is just holds the place for an argument, right? And with this, the interface description is complete. Now we can move on to the next part, the interpretation part, with the generated table on the right. What this table does is that it maps integers to the methods of the class. And this is very important for us, right? Now, how the interpretation actually works. Let's suppose that we get the data shown here from libFuzzer as a fuzz string. And what we will do is that we will take the first byte of it, interpret it as the ordinal number of the method to be called, and then we call that method. The number 0 was size. But the number 6 is push front. And we have a problem here, right? Because it needs an argument. It had an argument placeholder defined, which symbolized an integer. So what we could try to do is to take the next 4 bytes within the string, interpret it as an integer, of course, assuming that an integer is 32 bits at the moment, and we can use that result as a parameter. And we can continue this process with one being d.back. Now, there are a lot of edge cases here. We can have an integer that is too big as a method ordinal number. What if we get 121 at the first byte of the data generated? What if we have only 1 byte remaining and we want to generate an integer for an argument of a previous method, what is just now being called? And of course, these are things that we can reasonably work through, right? We can just write some code and handle these edge cases. But the great thing is that we don't really have to, because libFuzzer has just the utilities that we need here. Namely, what I'm talking about is fuzz data provider. Now, this class is defined specifically for consuming the fuzz string and interpreting it as different bytes. In this example shown, first, it is used to generate an int between 0 and 255 as the age of a person. And why I've specifically chosen this example is that the data that it's trying to generate fits on 1 byte, right? The range from 0 to 255 fits on 1 byte. And even though we are generating an integer, fuzz data provider is smart, realizes that the range we want to cover only needs 1 byte, and so it only eats 1 byte from the input. And this is not all that it can do. It can also pick values from an array, it can generate floating point numbers, it can generate fixed or random size strings from our bigger strings, substrings if you will. And this is a neat tool in my opinion, and its flexibility and ease of use is the reason why I've implemented argument placeholders as functions taking a reference of fuzz data provider and returning an instance of the type that we want to placehold for. This means that it can be easily extended by anyone if a type that your method might take is not supported by default by the auto test library. Now, we are at a place where we can safely generate test cases which have only valid method calls and roughly look like the 3 on the slide right now. But Are we satisfied really? What if we have bugs which are not revealed by crashes? Of course, we have sanitizers, but something catching actual logical errors might also be great, right? And what we can take to try help us with this problem is invariants. Now, an invariant is a condition which is always true as long as the object is in a valid state. It should be true from the construction of the object until the destruction of it. A method on the interface of the class can always expect it to be true when it runs, and even if the invariant might be broken while the method runs, it must hold once the method returns again. And how can we use this invariant? How can we use to easily check for logical errors? Well, we've already observed that unit tests are method calls with state assertions in between, right? On the left, we have the unit test example from the start of my talk. Now, what we can do is just take the generated test case and inject invariant checks between each method call that we have. Seems easy enough and might actually work, right? But of course, even though it looks great, sadly it's not as strong as manual assertions in unit tests. So of course, we have no chance of replacing unit tests. We can only add another tool to the testing tool case that we have. So let's put it into the test. Let's see how this method actually performs. The first data structure I've tested it on is a single-ended DEC. It's a single-ended variant of the data structure introduced at the start of the presentation. Although it's simplified to be way easier to implement, the main issues are the same as the ones we had with the actual DEC class. It still has to manage a growing vector of arrays, which can be a real source of problems. Now, Autotest managed to consistently achieve 100% code coverage within seconds on this class, within seconds. We can see the interface of the class on this slide. It's fairly similar to the standard DEC interface, only that it has only one end, right? And it is templated and has some trickier methods like universal referenced in place back. Now, this is how all the test code looks like. This is every single character that I had to write for testing this class, this container that I've written. First, it starts by the now so well-known precondition, right? Let's see whether the container is empty. And afterwards, we have an enumeration of the methods, practically just like we've seen before. We have mPlaceBack, which has the placeholder for an integral argument, which is of type int. We have popback, which requires the container not to be empty. We have back, which also requires the container not to be empty, both in constant and in non-constant forms. And we have a size method. And I was pretty happy about how it turned out. Now, the second example is a bit more complicated. I've chosen a state-of-the-art hashmap implementation, which is one of the fastest ones according to the measurements that I've seen. Robin Hood hashmap is a header-only library which is over 2,000 lines long. And when I started fuzzing it, it didn't have a satisfying result. It was fluctuating between 88% and 93% code coverage, reached within a minute. And I wasn't really happy about this fluctuation. But after some investigation, what I found is that the 5% code, which was only hit sometimes, needed the container to be really, really big. So what I did is that I fine-tuned the fuzzing parameters. Thankfully, for libFuzzer, how much the maximum length of a generated string grows with the amount of time that libFuzzer is running can be customized. So I've just modified the value to grow faster, and after that it will manage to hit 93% coverage all the time. Of course, after that I've also looked at the remaining 7%. Maybe we can do something else to reach that too. But I found that it wasn't really possible because all of it was explicitly instantiated template functions and a few lines of code which needed the container to be obscenely large. And so I was fine with not hitting any of that. Now, although at first I was planning to give everyone a free space here for the too much code on the slide place on their CPP bingo, but I ultimately broke the implementation of the hash map test into two parts. This first part is the setup. Here the argument placeholders are defined, which we will use on the second slide. We can see that it has a TORAS which will be used to resize and rehash the container to have a size between 1 and 10,000. The integral range on the right is defined as a function taking the start and the finish of the range and returning a functor taking a fuzz data provider which will return the actual generated integer that we want to use there. So this is just, TORAS is just an argument placeholder, and this stands for everything else in the slide. All three things are just argument placeholders. Random string is also implemented the same way. And in key-val, what we can see is an actual custom written argument placeholder when we use pre-existing argument placeholders, namely random string, and combine them to create a random string pair, which is the Robin Hood pair, not standard pair. Now what we can do with these argument placeholders is that we can just declare our methods like this. This is pretty boring, exactly the same as it was on the previous slide, only with different methods, right? We have an insert which takes a pair of strings and inserts the key value pair into the map. We also have in place which constructs the pair in place, as far as I know. We also have count, which counts the keys, contains, which checks whether the key is in there, and so on and so on. So I honestly think that the amount of user code that was necessary to implement this interface fuzzing as a user, right, is very, very small. And I'm happy how it turned out from an interface standpoint, to be honest, even though I couldn't leave out these auto test macros, which I honestly tried really hard, but just couldn't really succeed. So let's sum up what happened in the last, 40, 50 minutes, We encountered the problem of not having mass testing tools in our repertoire. And the solution we tried was adopting existing fuzzing methodology. So to do this, we first created a way to describe the interface of the class that we want to test. Afterwards, we interpreted the fuzz string as a method list and excluded the invalid test cases from it. We then executed the interpret test case. And what's great about this solution is that it works well with the same sanitizers that libFuzzer can be used with. So the first results of the prototype seem pretty promising, which were the ones that I mentioned in the case studies section. And if you would like to take a look at this prototype, feel free to look at it at my GitHub. The link is on the slide there. So the question is where to go from here. Well, a great idea would be to test it on non-container classes, which might pose additional challenge with the argument values meaning more than in case of the containers. Of course, this prototype, while it seems to work well enough, also needs a pretty big refactoring, because honestly, I'm really hoping that nobody will look at the code itself. But of course, the most important future work I have right now is to answer any questions you may have about the presentation. And hopefully I will be live in a moment.
Monoids, monads, and applicative functors. Repeated software patterns. Now, why would we want to talk about software patterns? Well, in a nutshell, it's this. You have your interface to your class, you have your implementation detail in the private section. What are you going to expose as your public interface? Well, in order to answer the question of what are we going to put in our public interface, we need to figure out what are the fundamental operations. Now, you've probably seen classes, God classes, with hundreds of member functions, but many of those member functions could have been implemented in terms of the other member functions. So what are the fundamental axioms of your type? And then what is the flexibility that you want to be able to provide your user given these fundamental axioms? When you do things in a functional design way, these are critical questions when you're designing your interface. And finally, when you apply some of these functional design patterns, you're going to be able to see how they relate to other classes. These are very powerful generic patterns, and there's a lot of composability with other classes. So, one thing I want to get straight right from the beginning is that functional patterns are not for the users. You don't expose something called the monadic bind operation. Why? Monoids, monads, and applicative functors. Repeated software patterns. Now, why would we want to talk about software patterns? Well, in a nutshell, it's this. You have your interface to your class, you have your implementation detail in the private section. What are you going to expose as your public interface? Well, in order to answer the question of what are we going to put in our public interface, we need to figure out what are the fundamental operations. Now, you've probably seen classes, God classes, with hundreds of member functions, but many of those member functions could have been implemented in terms of the other member functions. So what are the fundamental axioms of your type? And then what is the flexibility that you want to be able to provide your user given these fundamental axioms? When you do things in a functional design way, these are critical questions when you're designing your interface. And finally, when you apply some of these functional design patterns, you're going to be able to see how they relate to other classes. These are very powerful generic patterns, and there's a lot of composability with other classes. So, one thing I want to get straight right from the beginning is that functional patterns are not for the users. You don't expose something called the monadic bind operation. Why? A user is going to look at that monadic bind operation and say, what is this thing? I have no idea what this does. Your interface sucks. Now, that's not saying we shouldn't expose a monadic bind operation, but don't call it a monadic bind operation. Now, it may be at some point in the future, C++ users everywhere are going to be familiar with category theoretic concepts, and you can call it monadic bind, and they're going to understand what it does. But until that point, make sure you use good names. You can use the power of category theory, but you can also get an intuitive UI by making sure that you name your things in a way that your users expect. And one final note, writing generic code is a lot of fun. It's super fun. We're going to have some fun in this talk, but readable code is even more fun. Well, it may not be more fun, but it's better for sure. And certainly for you as software engineering profession, know that this is really important for you. So, a little bit of history about what we're talking about. You've all heard of the language Haskell. Haskell started out as an academic programming language, which is modeled after math. The folks that made Haskell got together and said, hey, we really love math. Wouldn't it be cool if we had a programming language that was basically math as a programming language? And let's see if we can make that efficient somehow. Now, purity is a really big deal in Haskell. This is what separates it from the other languages that were functional at the time, is that they stuck with purity. So what is purity? We're not going to go into too deep detail about purity, but basically a pure function, if you give it the same inputs, you'll get the same output every time, and there are no side effects. So they basically excluded side effects from the language from the very beginning and tried to figure out how far they could take it as a programming language. They used streams as the I/O model, but this was extremely cumbersome. And you couldn't really do powerful things in Haskell when it first came out at Haskell 1.0. So Haskell 1.0 was absolutely a toy language. And that's okay. These are researchers working on theoretical concepts. Practicality wasn't their goal. However, later on, monads hit the stage, and things started to change. In 1989, Eugenio Moji was looking for ways to describe the meaning of programs in an abstract way. And he discovered that category theory, a branch of mathematics, could be used to model state and exceptions. And that was fine, and a few years later, 1992, Wadler made the key discovery that monads from category theory could be used to express I/O in Haskell. And this was a game changer because this made Haskell actually useful. It was no longer a toy. So category theory becomes popularized in functional programming since. So you'll hear a lot of category theoretic concepts and all this, and it all came back to that 1992 discovery that monads can model I/O in Haskell. Now, category theory. What is this thing? As I mentioned, it's much older than Haskell. The investigation started in 1942 by Eilenberg and Mac Lane. What they were attempting to do was to abstract over various mathematical models. So back in your algebra class, you may have started with a bunch of axioms for math, and you tried to prove out all the other things that we know about mathematics. This was very common at the time, and there are different sets of axioms that you can use in different domains to make varying mathematical models. Category theory was all about figuring out how you can abstract over all the different models. So it was extremely, extremely general, and it made it applicable to many domains, even outside of mathematics. Music theory, for example, is something that has made use of category theory because of its generality. So when we talk about in computer science patterns, usually we're talking about things like factory and singleton and all these other things that are really based on utility. It just seems like something in the toolbox that a lot of people go for frequently, and that's totally cool. But what we're talking about in terms of design patterns is something fundamentally different. We're talking about patterns that are discovered in nature. These are not going away. They are not transitory. These are related to the physical laws of the universe, and they can impact how you design your programs. Now, when you hear words like category, functor, duality, monoid, isomorphisms, etc., all these words are associated with category theory. We're not going to cover all of them. We're only going to look at a few of them, and then you can go on after this talk and do your own investigation and research and discover the wealth of interesting theoretic concepts that can apply to your to your designs. Now, we're going to start taking a look at the first of our category theoretic concepts, which is called a monoid. So a monoid is a type in combination with a binary operation. A type T, some kind of binary operation, which is like a cross with a little circle in it. Now, the binary operation combines the values. Now, in order for a type combined with a binary operation to be considered a monoid, all you have to do is have these two properties. First, that operation needs to be associative. A op B op C is the same thing as doing B op C and then doing A op that at the end of it for every single value. Now also, this type needs to have a special value E such that E op X is the same thing as X op E, which is just X. In other words, it's the identity operation. When you apply it to the operation, you get this almost like an identity function. Does that all make sense to you? Okay, well, let's try to break it down into a simpler example here. So, numeric types, like numbers. All right, we're not doing any programming yet. We're just talking about numbers. We have A plus B plus C. If you do A plus, the parentheses around A plus B first, A plus B plus C is the same thing as A plus B plus C if you put the parentheses around B plus C. Does that make sense? Okay, good. Now, what should be the special value? What do you put plus any number to get that number back?
0.
Yes, exactly, 0. So we have the numeric types, and we have the special value 0, and you put these together with plus, and you get a monoid. All right, now let's see who can take a gander about what the monoid would look like if we had numeric types with multiplication. Well, the first question would be, what is the special value? What do you multiply by any number and get that number back?
You multiply anything by 1 and you get the same thing back.
Yes, exactly. You got it. You got it. That's exactly what it should be. So the numeric types with multiplication are monoids if you look at 1 as the special value and you use just the multiplication operation, which has the property of A times B times C equals A times B times C no matter where you put the parens. Cool. Now, what about an unsigned number with stood max as the operation? Well, if you take a look at that property of, max of max A, B, C is the same thing as max of A, comma, max of B of C. Okay, that totally makes sense. What would be the special value for max with an unsigned? Max of anything in this number gives you the other thing.
0.
Yes, Carmen. Yes, exactly. 0 is the special value in that case. Absolutely. Great. So now we're being able to discover more and more monoids. And let me tell you, monoids are absolutely all over the place. Now, one other question that you might ask is, and I'll leave this for an exercise. Kids, don't give the answer away, because I want the people on the screen to do it. The question is, what is the E value for the float, comma, stood min monoid? All right, you guys in the audience that aren't my kids, please figure this out and think about it. It's actually quite an interesting answer. Now, here's another question. Does stood vector form a monoid with something? Think about it. What would a monoid, if vector were a monoid, what would the operation be?
Concatenation.
Yes, that's exactly right. Basically, with a stood vector, if you have a vector and another vector and you just concatenate their contents, that actually forms a monoid. And what would be the E element for the monoid in that case?
The empty vector.
Correct. Now, what could you do if you had a list or some kind of collection of monoids? What would be some kind of operation that you could do on such a thing, knowing only that it's a monoid?
Squash.
That's right. You squash them. That's the thing about monoids, is that you can basically squash them together, whether you have 0 of them, in which case you produce the E element, or you have a bunch of them. Now we're going to talk about some fancy monoids. Now, stood optional template. A stood optional, which you all know, is either null or it has a value of type T. The question is stood optional a monoid?
Yes, because you're asking.
Yes, it's a monoid. So what would the monoid operation be like?
If it's an optional of a monoid, the optional monoid is a monoid. Use the underlying operation on the optional contents, assuming it has some.
Yes, exactly. A stood optional monoid is a monoid. So if you have a stood optional of a monoid, that is also a monoid. And the way that you do the operation is if the left-hand side is empty, then you choose the right-hand side. If the right-hand side is non-empty, then you use the monoid operation of the left-hand side and the right-hand side. Otherwise, you just choose the left-hand side. In other words, if they both have something in it, you squash the two things on the inside to get your optional monoid. Now, another stood optional monoid would be, for example, this, where you can take essentially just always prefer the right-hand side. That also would form a monoid. There are a few different ways of doing this, really. So here's a more complex question. Do functions returning some value form a monoid? Functions of the same type that return a monoid are also a monoid. And here's what that function would look like. You essentially have a function called append, which takes in two functions and returns a new function based on the results of the two functions in the input. So it builds a lambda function on the inside that takes in any value a, and the results of that lambda function takes the left-hand side operated to a, monoid operation of the right-hand side operated to a, and squashes those two together. And that's how you can have a function that returns a monoid, that the set of functions which return a monoid actually form a monoid themselves with this kind of operation. And the empty element, of course, is going to be the function which takes in any value and always returns the empty element of the monoid. Let's say you want to search for the n best occurrences of a word in 1,000,000 documents. The key insight here is that an n-heap data structure is a monoid. An n-heap, in case you weren't familiar with it, is basically a list of the best elements, for some definition of best, and according to like their goodness criteria. And you can take n-heaps and combine them together to get other n-heaps. And this is a monoid. You can split documents between your cluster nodes. You send the word to each of your cluster nodes, which has many, many documents. Each cluster node generates its n-heap using internal parallelization, and then each cluster node sends its heap to a collection node. The collection node just joins the heaps using the monadic operation. key insights here that we're getting about monoids. They scale very well. They compose via functions and optional and other things. So remember when we talked about how does the observation of something being a category theoretic concept apply to other classes when you compose it. And monoids are very, very common. Functors. So unlike monoids, what we were looking at before, functors are not individual values. It's best to think about them as class templates. So a functor is a class template with a single template parameter. And in addition to this type, you have a callable called map. Okay? And map has the following properties. Map takes in a function as its first argument, let's say from A to B, and it takes in a functor as its second argument. So let's say it's a functor of type A. And what it returns is a functor of type B. So there are different rules associated with this. If you take in an identity function, so a function that always returns this argument as the first argument of the function that you pass into map, that will not change the functor that you pass in as the second argument because it returns the new functor. It also has some composition rules to make sure that applying a function to a functor, calling map 2 times with 2 different functions, is the same thing as composing the functions first and then calling map of that. But let's build up some kind of intuition for functors. Functors are a lot like containers. Map applies a function to the thing in the container, resulting in a new container of the transformed values. Transform, for example, if you're familiar with that standard algorithm, is like map, but for containers. And the laws provide these reasonable rules for map composition. So std vector is a functor. What happens what is the map function defined for std vector? So map takes in a function, let's say from t to u, and we have a std vector of u as the second argument of map. What does it do? It creates a new vector for the return value, and that new return value just applies f to all the values in the input parameter. Okay? So again, we're just transforming the values inside of the vector. That's an intuition for vector as a functor. What about std optional? Is std optional a functor? What do you think?
Yes, it is.
It is, indeed. And what would its map function look like?
If the optional is empty, return empty, but with the result type. If it has a value, then apply f to the value and wrap that as an optional.
Yes, exactly. Map takes in a function and an optional, and if the optional is none, then it returns a none optional of the transformed type. But if it has a value inside the optional, then it returns a new std optional value by applying the function to the thing inside the optional that was part of the parameter. Exactly right. What about std pair? Is std pair a functor?
Seems like it should be somehow.
Yes, it does indeed seem like std pair should be a functor. But remember that functors have one template argument which is changing. So with the case of std pair, what we want to do is take that first template argument or the second, depending on how you define your map function, and fix it. So the first parameter in a pair doesn't change, or the first value in a pair doesn't change, and the function is applied to the second part of the pair. What about std function? Is std function a functor? And it turns out std function can be a functor if you fix all the parameters of your std function so that every single function has a fixed set of parameters, and the result of the std function is that changing type. So you build a new function which transforms the result of the old function. And this is what a map function would look like for a std function functor. Functors allow for transformations within the type. Each map strips away one layer of your data type. If you're working with a std vector, you can strip away the vector part of it by using map to get to the thing on the inside. So say you have a std vector of std optional of int and want to get strings for each int. Look at this function and how it's defined. So f1, all it does is it converts an int into a string. f2 uses the map function to convert an optional int into an optional string. And then f3 converts a vector of optional int to a vector of optional string. So you see how we're just building these maps, and each map subsequently gets you to the innermost thing. That is how you can compose various functors of functors of functors and get to the thing on the inside. It's a very powerful composition. Now let's take a look at applicative functors. An applicative functor is a functor with two extra operations, pure and apply. Now, pure and apply have the following rules, but basically pure, the way you can think about it, is a way for you to create a new applicative based on a plain value. So let's say optional is an applicative functor, which we'll find out it is in a minute. If you call pure of 3, you're going to get an optional of int. Apply, this is something that applies a applicative of a function to an applicative. So remember how map, you took just a plain old function from A to B and you applied it to the functor of A to get the functor of B. The difference between that and apply is that apply takes an applicative of the functor and applies it to an applicative value to get a new applicative value. Now we'll look at some examples of this to make it more concrete in a second here. Now, applicative functors have a bunch of laws, and I'm just showing them here to you for your own interest. I'm not going to go over these laws. It does what you would expect it to do if you try to think about what would be the natural laws for an applicative functor. Now, the intuition behind applicative functors, as I mentioned, pure wraps a value into a container, apply applies the contained function to a contained value to get a contained result. And if you think about it, apply can be extended to n-argument functions by doing some additional work. You can base an n-argument apply on a single argument apply. I'll let you think about that as an exercise. So the std optional applicative functor. So pure for optional looks like this, which is of course no surprise. You basically take the value, you put it into an optional. Now what about the apply function? So the apply function, if you think about it, you have the applicative of the function and you have the applicative of the value. So you have an optional function and an optional value. If they both happen to have a value, the optionals is not none in either case, then you apply the thing on the inside of the function argument to the thing on the inside of the value argument, and then wrap that into an optional. If either of them happen to be null, then you just return null. How could this be interesting? Consider this snippet of code. Here we have optional double of A equals some computation, optional double of B equals some other computation, optional value C, you apply plus to the optional double of A and the optional double B, and then D you apply negate to the optional value C. What's going on here? Let's say A is null. What is D going to be? Null. Let's say A isn't null, but maybe B or C turns out to be null. Or actually, let's say B turns out to be null. Well, then the answer would be null. So here what we're seeing is that if you think of null as being an error condition, is a way for us to propagate errors throughout a program. And this isn't the first time this has been discovered. It was discovered a long time ago that applicative functors have this kind of error propagation behavior when you use them with std optional. Interesting stuff. What about std vector? Is std vector an applicative functor? Well, is it a functor? Well, we know that it's a functor. We know what map is for a std vector. What about pure? Well, pure for a std vector could very easily be just create a vector with one element in it of that value. That makes complete sense. What about apply, though? You've got a vector of functions and a vector of values. What can you do?
Apply every function to every value, and you put the result in a vector.
Exactly right. You can apply each function to each different value. For function 1, you apply it to all the different values. For function 2, you apply it to all the different values, and so on until you compute a vector of all the results of all the functions applied to all the values. So what is this? What is this model? Well, think about it. Let's look at this code snippet here. Here we have a vector of doubles A and a vector of doubles B. And what we do is we apply stud plus to A and B. And of course, we're doing the n argument version of apply here. What you get are all the different possible ways to add vectors of A and vectors of B. This is non-determinism. The applicative functor for stud vector models non-determinism. Now, there are a lot of different applicative functors. Stud future is one. Continuations, exception style errors, behaviors in functional reactive programming, of which I'd love to speak more about that one time, or parsers, etc. So functors apply all over the place and are a very key, interesting example. Now let's take a look at parser applicative functors. These are a very interesting use case of applicative functors. The idea here is to be able to build an interface for our parser library and utilize category theoretic concepts as a means for us to build a very powerful parser and give us that minimal set of operations that we want to have, of which you can build everything out of. So, what are the fundamental operations for a parser? So, we'll start by defining our type, parser of T. It's just a stood-in parser that parses into type T, let's say. This is simplifying. In reality, you probably wouldn't want to hard code it to be stdin, but for our purposes, this is just fine. So if P has a type parser of T, P.read tries to parse stood-in. If it succeeds, it returns type T. Otherwise, it throws an exception. You probably want to do something other than throw an exception for your error handling, but again, for simplification, we're just going to do it like this. Now, this particular parser is implemented by having a collection, a vector of chars, which this parser knows that it can parse based on these chars. This will help us with composition later. So if you say, your parser can read, is only valid, if it begins with the letter A, then this vector of chars will have the single value A in it. And it also has a Boolean, which just tells you whether or not this parser consumes nothing. If it consumes nothing at all, then this Boolean will be true. And then, of course, you have this stud function in there, the function which actually does the reading. So in our case, the function has no parameters and just returns the value of type T. All right, that's our type. We're going to create some friend functions here. One is a parser which reads a single character from stood-in, any character. Okay, so we just call that char P, and it returns a parser of char. We also have a char P which takes a particular character as input and returns a parser. So this is a parser that if it reads in that character, then it's successful. If that character is not found in the input, then it will not actually parse it properly. And then we have an either function here. So either, what it does is it takes in a parser of type A and a parser of type A, so two parser of type A's as parameters, and produces a parser of type A as a result. And what happens is if LHS, that first parameter there, fails to read for some reason, then it will use RHS. All right, makes sense. So it's using either LHS or RHS will be just fine. And then finally, we have 0 or more. So this is a primitive here that says it will read 0 or more values of type A. Okay, so that way, if the 0 or more, it takes in a parser of type A and returns a parser of a vector of A's by just reading as many A's as possible. Let's see how either would be implemented. Either here, it takes in, as I mentioned before, a parser of type A and another parser of type A. Consumes nothing is only true if LHS consumes nothing. Because if LHS consumes nothing, then it's just trivial. It's always LHS, and that's the end of it. Now the start character here, it will append the start characters from the left-hand side to the start characters of the right-hand side. And that'll be the start characters that are valid for the either of the two different parsers. Now, what about reader? What happens with reader? It reads one character from std_in. It tries to see if that left-hand side parser can support that character. If it does, then it just returns left-hand side.read. Otherwise, it returns right-hand side.read. And then overall, then we take this combined function and we return the result. What about pure? So here we need to be able to create a parser t out of a value t. Pure in this case would be a way for us to just say it always succeeds, so consumes nothing is true, and produces a value, this particular value that you pass into the success p function. Note we didn't call this pure. We called it success p, going back to the idea that you want to make sure that you provide a vocabulary naming that makes sense for your domain, even though you happen to be pure under the hood, using these category theoretic concepts. What about apply? We know that this is an applicative functor, so basically because I told you, but how does apply work? Apply takes in a parser of a function, right? And it takes in a parser of a value, applies the parser of the function, the inside of that parse function to the inside of the parsed value. Even though nothing's actually been parsed yet, we can still compose these things together. Consumes nothing would only happen if the function parser consumes nothing and the t parser consumes nothing. Now let's say the function parser consumes nothing. So the start character is going to be equal to the value parser start characters, right? Otherwise, it's the start values is going to be the function parser start characters. What about the reader method? So what happens is we call the function parser read to get that function, and we call the value parser.read to get the value and return f of t. And then finally, we return the result. Okay, pretty straightforward. You may not know how we would use apply, you may not know how you use pure, but considering, let's see where this takes us, considering it matches this type theoretic concept. So it turns out that we're done. That everything else that you would need out of this parser can be built on these pieces. Let's take a look at digit p. So here we want to have a parser which parses a digit. So first we create a lambda function which converts a character into an actual number. No problem there. And then we want to be able to parse in the individual characters. So we have char p0, char p1, and so on and so forth, all the way into char p9. All right? We use either to be able to say that any of these individual parsers work. And then we use apply to convert that parser so that either parser, remember, is going to return a parser of char. We change that into a parser of int. So we're just taking these fundamental pieces and applying them together, and we're able to build out a digit parser. Now, what if we want to have an int parser? We can use 0 or more digit parsers, and so on and so forth. There's even ways for you to be able to take two parsers and say, hey, this is a parser of a pair from A to B by getting a parser of A and a parser of B. You can use apply for that. And putting all this together, if you want to have two ints separated by a space, you can take that function that we just used and just make parse an int, parse a space, parse another int. So are you starting to see how you can build these powerful, powerful libraries by using these fundamental operations? That's the idea. Let's review this. Monoids. What are monoids good for? These are highly parallel patterns. In fact, it's a generalized version of MapReduce. If you find that the domain you're working on happens to model a monoid, then you know you can apply a MapReduce kind of like system to work this in extremely parallel terms. What about functors? Functors, you do things to the stuff inside. And you can thread functors of functors of functors to get to the thing on the inside. A very powerful abstraction. And applicative functors. This is a way for you to put stuff inside, and the stuff inside can do things to the stuff on the inside. In other words, the apply function. Now we look at monads. Now a monad is an applicative functor with one extra operation called join. So join takes in a monad of t and produces a monad of t. And that's it. A monad is simply an applicative functor with a join operation. Now, there are monad laws, and it's a bit more complex to express these in C++, so I'm not going to throw them on the screen here, but I will say, please go to this link the category theory webpage there, and you'll be able to understand how this works for Haskell, and you could intuit how these monad laws would apply for C++. Now, what would join look like for stood optional? Join, remember, it takes in the monad of a monad of T, so in this case it would be an optional of T. Join, what it will do is take an optional of T and build an optional of a T out of it. The implementation is probably exactly what you would expect it to do. Pretty simple. What about other monads? There's stood vector. There's a parser monad. Now, the parser applicative functor that we made before is different than the parser monad. Our parser doesn't have the ability, as a model as an applicative functor, to be able to start with a parser, parse a parser, and then apply the parsed parser to the input, right? So imagine a parser where the first thing it does is it parses the language for the rest, parses the parser that's supposed to apply to the rest of the language of the input. Applicative functor parsers can't do that, but monad parsers are, so that gives you that extra power. Functions with a single parameter of type A actually are also a monad. So what's the big deal? Who cares about monads? It just seems like it adds one thing to applicative functors. Well, this bind operation. So I talked about it way back at the beginning. Don't expose your thing and call it monadic bind. Well, the monadic bind operation is defined in terms of other operations. So for a given monad of T, in order to be able to construct a bind, you use pure, apply, and join. Usually, for bind, you want it to be an operator overload. Let's use the right shift operator. Here we have an optional of int getInt function. And here we use the monadic bind to be able to start with getInt. You have some kind of syntax. GetInt, you have some kind of other syntax. GetInt, you have another kind of syntax, and you call pure of A plus B plus C. If you indent this a little bit differently, it looks like this. Now, if you squint, you might see something like this, which, if you cross your eyes, looks like this. In other words, this looks a lot like imperative computation. And that was the original reason why monads got so popular in the first place, is because it looks like imperative computations. And that was a really big deal for Haskell. But what about us? Does it do anything for us in C++? Well, what monads allow you to do is express different models of computation within C++. Stood vector gives a language with non-determinism. Stood optional provides a language with error fall through. There are continuation languages. It also allows you to provide more control over computation. You could take a computation which is expressed in monad form and serialize the computation itself, and then deserialize it and use it. You can have a command pattern embedded language. It is also extremely interesting for imperative template metaprogramming. So let's wrap this up. The first thing to note is this is just the beginning. There are more interesting patterns: semigroup, category, arrow, comonad. All of these can be used to enhance your design skills. Now, I will probably do a subsequent talk at one of these conferences at some point to talk about more examples of these things. But here is your base knowledge of very common repeated software patterns in functional design. Now that we've finished, let's go and take some questions.